Um, in the homogeneous catalysis, we said there are about 5 different steps. And if you recall, we said the first step is ligand association and dissociation. We gave examples of that. We talked about insertion and elimination. That is another step. And then the nucleophilic attack on the coordinated ligands, oxidation reduction, and finally oxidative addition and reductive elimination. So these are generally the steps that are found in most of the homogeneously catalyzed chemical processes. So today we will talk about some real life industrial processes, and we will also get into the mechanistic aspect of how these reactions are carried out and what are the steps involved in the catalytic processes. All right, so the first example that I'm going to give you is a very important industrially profitable reaction where you have paratoluene, which is basically you have that's a xylene. Now that is getting oxidized to terephthalic acid. This is a very important, commercially important reaction because terephthalic acid is the monomer people use for making plastics. I mean, your PET bottles, right? Water bottles, the plastic bottles are made from petroleum. So basically, what they do is they take the paraxylene and then they oxidize it to 1,4-benzene dicarboxylic acid, which is also known as terephthalic acid. Once you take the terephthalic acid and do the polymerization with the ethylene glycol, you get what we call polyethylene terephthalic acid, or PET bottles, essentially. So we will now look into how this reaction takes place and how the oxidation and reduction properties of the transition metals help us achieve this both quantitatively and highly selectively. All right, so let's see how this reaction goes. So let's call most of these hydrocarbons as RH, where you have the hydrocarbon and the proton. So for example, you can take one of the hydrogens of the methyl groups on the benzene as this hydrogen here. So the first step in the process is what we call the radical initiators. So essentially what we are doing is we are taking this molecule and making a radical of this. So we get an R radical plus the indicator or the initiator with the hydrogen there. Now, next step, what happens is the radical that we have here reacts with the oxygen to make what we call peroxy radicals, ROO dot. That is a radical. And in the final step, what happens is the peroxy radical reacts with one of the second molecule, and then we get ROOH plus R dot. So we call these reactions 1, 2, and 3. If you can see this. So what happens is, on the second step, we make this peroxy radical. The peroxy radical reacts with one of the original hydrocarbons and then makes the carboxylic acid and generates the radical. This radical again goes back in step number 2, reacts with excess oxygen, again makes this. So this process goes continuously with steps 2 and 3 repeat themselves infinitely. In the process, what happens is we get the carboxylic acid. This is how the radical initiated oxidation of paraxylene to terephthalic acid is carried out. But one of the biggest problems here is once you have these radicals, as you can see, you have R radicals, you also have peroxy radicals. These radicals can undergo what we call termination processes. Okay, let's see how the termination happens. The termination can be let me write down this separately here for clarity. Termination can be one of the R radicals can react with the next R radical to make R2. When that happens, the R radical cannot react with oxygen to make this peroxy radical. So basically what happens is this termination reduces the concentration of the R free radicals, and hence the reaction will not go quantitatively. So that's a big problem. The second big problem we have is one of the radicals or radical can react with the peroxy radical here and then make ROOR. That is not the intended product. The intended product is a carboxylic acid, not an ester like this. So this is something that we have to deal with. And finally, we can also have two of these peroxy radicals to give what we call superperoxy radicals like this, which will break down into oxygen and non-radicals. So here is the mechanism on the top, and here are the problems with the mechanism, because if you were to generate free radicals, these free radicals can terminate themselves in one of the three ways. So you can have the R radical reacting with the R, giving you R2. That is not the intended product. Similarly, R radical reacting with the peroxy radical to make this ROOR. That is not the intended product. Finally, two peroxy radicals can give you super peroxy compounds, which break down instantaneously to make oxygen and non-radicals. So how do people get around the situation? This is where the inorganic chemistry comes in. So if somehow you can preserve the RO radicals, the peroxy radicals, then there is a good chance of making the reaction happen. So in industry, what they do is they take the ability of the transition metals to exist in multiple oxidation states. So let me now go over that chemistry. As you know, if you have copper, copper can exist in 2+, 1+, and 3+ states. So that is a redox chemistry there. Copper can exist in 1, 2, or 3 oxidation states. Similarly, cobalt can exist in 2 and 3 oxidation states. Nickel can exist in 2+ and 3+. Iron can exist in 2 and 3. Manganese can exist in 2, 3, 4, and 7 too. So the ability of the transition metals to exist in multiple oxidation states points to their ability to serve as oxidizing or reducing species. And we understand these properties from the previous lecture, where we extensively talked about the redox properties of the transition metals. Now, we're going to use those redox properties to tailor the oxidation of paraxylene to terephthalic acid and control the termination process. In other words, we will block the termination processes using these transition metals. And once you block the termination processes, then the free radicals are effectively utilized in making the intended product. So here is how that is done. So in the industry, in the oxidation of paraxylene to terephthalic acid, they take cobalt in 2+ oxidation state. Watch this very carefully. This will react with the carboxylic acid to make the cobalt carboxylic acid complex, and it also produces in cobalt 3+ state hydroxides and RO radicals. So this is how the cobalt 2 is now oxidized to cobalt 3. So this is the ability of cobalt to exist in multiple oxidation states, which is helping us to make these RO radicals. And the next thing what happens is the cobalt 3 that we made in the previous step can react with the ROOH to make cobalt 2, and we have RO radicals plus H plus ions. So if you look at this second process, the beauty of this is this cobalt 2 will react with the carboxylic acid, come back and generate more peroxy radicals here. These radicals again go back into the original process and make the carboxylic acid. So without the cobalt 2 plus added into the solution, the efficiency or the quantitative yield of the process is very small. But adding a very small amount of cobalt, the ability of the cobalt to shuttle between 2 and 3 oxidation states generates these radicals, which are otherwise lost in the termination process. So this is how in industry they do this process. So the oxidation reduction plays a very important role in the homogeneous catalysis paths. Right? So this is an example of the oxidation reduction. Of course, in industry, people can use manganese, cobalt. The next thing is, of course, the cost aspects and the toxicity. For example, nickel also can do this process, but nickel is an environmental toxin. So you want to stay away from toxins, especially if you are preparing compounds in industrial scale, where you're making tons and tons of the compound. Cobalt and manganese have similar redox properties, but whenever possible, people prefer the manganese because manganese is much cheaper compared to cobalt. So in industry, sometimes what they do is they mix the cobalt and the manganese and make a combined catalyst to facilitate the oxidation of xylenes to carboxylic acids. Are we clear here, folks? Any questions? See how beautifully we have designed these processes to make selectively with very high yields the terephthalic acid, which is essential for making plastics, not only plastics, but nylons, synthetic fibers. These are all made using this process. Yes, Gurveer, you have a question?
Yeah, do we have to remember all these reactions?
No, you need to understand what is going on, that's all.
Okay.
You don't have to memorize these processes, no. When we finish this discussion, I'll tell you what kind of knowledge I would expect from you guys, okay?
Okay,
So
thank you.
given any process, I would like you to comment on what is going on here. So for example, when you see this reaction, the salient feature, the most important aspect of this process is the oxidation of cobalt to cobalt 3 plus and the cobalt 3 plus shuttling back to cobalt 2. So the main feature of this process is the ability of cobalt to shuttle between 2 oxidation states. In other words, this is an example of the importance of oxidation and reduction in homogeneously catalyzed reactions. So this is not insertion, this is not elimination, this is not an attack on the coordinated ligands. Remember, we talked about 5 different processes in homogeneous catalytic processes. So whenever an example like this is given in the exam, you must recognize this is a classic example of oxidation and reduction. Did that answer your question, Gurveer?
Yes, thank you.
All right, good. Okay, so the next step is what we call oxidative addition and reductive elimination. In fact, oxidative addition is just the opposite of reductive elimination. Or if you like, reductive elimination is just the opposite of oxidative addition. So in general, what happens is if you have a complex of 4 ligands and a metal, generally square planar complexes under this oxidative addition and reductive eliminations. And when you add a species, It could be methyl iodide, like A could be methyl, X could be iodide, or it could be simply a homonuclear diatomic molecule such as hydrogen. So HH is another thing, another example. What happens here is when you add them, because this is coordinated the unsaturated complex, because you have only 4 ligands, where you can technically place 6 ligands. So this now leads to the formation of this. So what happens is the AX breaks down and then forms the 2 ligands, A ligand and the X ligand. In general, most of them are anionic ligands here, which implies that the metal here gets oxidized. In some cases, what happens is just the opposite that happens, where AX leaves, giving you the square planar complex again. During that process, the electrons are given back to the metal, so that is a reduction here. So reductive elimination and oxidative additions are also important class of homogeneously catalyzed chemical processes. Am I clear here, folks?
Wait, so I guess the AX is acting as a nucleophile.
Right.
Okay, so the metal is getting reduced.
Metal is getting oxidized here. So I'm sorry, this is the oxidation process here. That is the reduction here. So I'll give you an example, real life examples. Although this is a template, but once we get to the real life examples, you will see the idea here. Maybe I'll give you a simple example here to clarify. So let's say instead of AX, we have hydrogen. Okay, in which case you're adding 2 hydrogens here. So once you add 2 hydrogens, what happens to the oxidation state of metal here?
It will decrease, right?
Decrease or increase?
Sorry, increase.
Huh? It must increase because this is a hydride ligand, right? So it needs an extra electron. That extra electron comes from the metal. So once the metal loses an electron to hydrogen, it gets oxidized. On the other hand, if you look at the reverse of the process, this is a dehydrogenation process here. In the dehydrogenation process, the hydrogen will give back the electron back to the metal, so it gets reduced. So if I have, instead of metal, we can say rhodium 1 complex, right? Rhodium 1 complex, when you add hydrogen, it moves to rhodium 3 complex, and the rhodium 3 complex will reductively eliminate the hydrogen to give you the rhodium 1 complex. We'll give you several examples of how beautifully this happens in coordination complexes. But this is one of the classes where you have a ligand forms a complex by oxidizing the metal. Am I clear here, folks? Of course, we're going to give you several examples. Today, I'm going to bore you with a lot of examples of industrially relevant homogeneously catalyzed processes. Any questions so far? All right, so we will start our journey into homogeneously catalyzed reactions that are of industrial importance. The first one I'm going to talk about is what we call hydroformylation. Have you heard of this process from your organic classes? Hydroformylation is a very important organic process that is used in petrochemical industries, especially when you have unsaturated olefins and you want to make aldehydes from them. Does anyone remember this process? Hydroformylation. No? Should I complain to your organic professor saying that why didn't they tell you about this?
Is it just another word for hydrolysis, or am I thinking of something else?
Hydrolysis is different process. That is basically adding water, right? If you really look at the name of the process, the name tells you all. This is hydrogenation, which is the hydro part of it, and formaldehyde, right? Aldehyde, basically. So you're doing two things at simultaneously instead of having two different reactions. This is a more like, if you like, it's a one-part process where you take an unsaturated olefin and then add carbon monoxide and hydrogen. So what you're doing is you're saturating the unsaturated bond using hydrogen. In the process, you're also adding carbon monoxide and converting that to aldehyde. So let me give you a classic example of a hydroformylation process. So here we have unsaturated olefin, okay? And then we're adding carbon monoxide and hydrogen. In the process, we make what we call or CH2, CH2, CHL. Watch the complex industrial process here. You have an unsaturated olefin, you're adding carbon monoxide and hydrogen in the presence of a catalyst. If you don't have a catalyst, nothing happens here. You can mix carbon monoxide, hydrogen, and this olefin, and you can wait for a million years, nothing happens. But as soon as you introduce a coordination complex of the right metal and the right ligands, suddenly you see this reaction happening in a very high yield and in a very selective way. So we're achieving two processes at the same time, and industry loves it. Anytime you can cut down 2-3 steps into one step, they'll love it because it saves a lot of money and it's also environmentally friendly. So there are lots of reactions. So most of the aldehydes industry are produced like this. So I'm going to give you the reaction mechanism. So you have to follow me very slowly. I'm not going to rush through this because this is, in my opinion, one of the very beautiful examples of the coordination complexes serving as a homogeneous catalyst. So let me start with the catalyst here is cobalt carbonyl. So it's a bimetallic catalyst or a bimetallic complex, which implies that there are two cobalts. Each cobalt is coordinated to 4 carbonyl ligands. So that is your catalyst. This, I would not say this is really a catalyst. This is a catalyst precursor. What happens here is when you add hydrogen to this, remember the hydrogen that is required for the process? So what happens here is you suddenly make 2 cobalt HCO4. So we have 4 carbonyl ligands, and we have hydride as one of the ligands here. And then, excuse me, okay. So this is your catalyst. And this is the one that enters the catalytical cycle. So here is how we start with this cycle. We start with cobalt hydrocarbonyl complex. And this one, in the first step, loses one of the carbonyl ligands. So when you do that, you get COHCO3. Instead of having 4 carbonyl ligands, now I have only 3 carbonyl ligands. So what I did was I kind of removed the carbonyl here and made an empty spot for another ligand to come. Now this time my ligand that is going to replace the carbon monoxide is, let's say, ethylene. That is the unsaturated olefin that we were talking about in the previous example. So when you do that, you get H, CO, CO3, and we have CH2, CH2. That is the new ligand that attaches to this complex. So now you can see there is a ligand elimination and a ligand addition here. This is a classic example of ligand association dissociation in homogeneously catalyzed processes. All right. In the next step, what happens is the CO that is lost in the second step is now coming and attacking this complex. In doing so, what this basically does is the carbonyl will go there and the proton will be transferred to the ethylene. So we get CO, CO4. There's a proton migration here that migrates to this, and you get CH2, CH3. Okay, so that is how the olefin is saturated there. And the next carbonyl ligand, remember the reactants here are ethylene, carbon monoxide, and hydrogen. So this carbon monoxide now goes and gets inserted between the cobalt and the ethyl groups here. So we get CO, CO4, and C double bond O, CH2, CH3. This is what we call insertion of a ligand. So one of the carbon monoxide molecules is getting inserted between the cobalt carbonyl complex and the ethyl group here, and in the process makes this fragment. Now, this fragment now, in the presence of hydrogen, gives you CH3, CH2, CHO. So what's happening is one of the hydrogens of the dihydrogen molecule attaches to the carbonyl group here, making the aldehyde, and the next hydrogen molecule attaches to this cobalt, producing the original complex here. So this is the entire catalytic cycle. This repeats, and sometimes the turnover frequency, that is the number of reactions that happen in 1 second, can be 1 million or more. That is how fast it turns around. It's highly selective and extremely efficient, happens at moderately low temperatures and very low pressures of carbon monoxide and hydrogen. So this is a very commercially important process. So to go back, we start with a bimetallic catalyst. This is called, in fact, a catalyst precursor. This is not exactly a catalyst. This is a precursor. This precursor, in the presence of hydrogen, breaks down to give you 2 of this cobalt hydrido carbonyl complex. This now loses one of the carbonyl ligands and makes a ligand deficient complex. This ligand deficient complex now adds on to the unsaturated olefin. Although I gave you an example of ethylene here, you can pretty much substitute that with any unsaturated olefin. And that one binds to the cobalt. And the next step, what happens is when you add the additional cobalt, carbon monoxide, that attacks this ligand, and the proton gets migrated to the unsaturated olefin, giving you the ethyl fragments. And the next carbon monoxide molecule that is added gets inserted between the cobalt and the ethyl group, and the hydrogen molecule now gets split in. One of the hydrogen goes with the cobalt to make the original catalyst, and the next hydrogen adds to this carbon to make the aldehyde. So how beautiful it is, you see. Am I clear on this? Any questions?
Where did the CO4 go? The after you add the hydrogen in the last step, where does the cobalt CO4 go?
Where does what?
Where does the CO in parentheses go? The carbon monoxide before those, yeah.
Okay, when you have the hydrogen, right? So it is how you can write. Hydrogen is H, right? one of the hydrogens goes here, the next hydrogen goes there. So you get CH3, CH2, CHO, which is what I wrote here. And the next hydrogen attaches to the cobalt and makes this original complex.
Oh, okay, yeah, that makes sense. Thank you.
Okay, so this is the beauty of it. So once you follow this cycle a few times, you see there are different steps that we talked about: ligand dissociation, right? We talked about redox properties. We also talked about, so whenever you add hydrogen here, you are going to reduce the cobalt. When you remove the hydrogen, you're going to oxidize it back. So this is how the whole thing operates so beautifully, so efficiently, so nicely. And it not only works for just ethylene, pretty much you can take any unsaturated olefin and then add carbon monoxide and hydrogen. You can do both the, the double bond is unsaturated, one is saturated right there. And then you also add a aldehyde functionality here. Once you have the aldehyde, you can oxidize them to make the carboxylic acids, right? Or you can also make primary alcohols. So there are a lot of things that you can do. These are mostly organic transformations, but the heart of the process is a hydrido carbonyl cobalt complex. Am I making sense here, folks? So given this process in the exam, sometimes we will characterize this as the step number 1, step number 2, step number 3, 4, 5, and 6, right? So we'll ask you, what is step number 1 here? What do we call this? Remember, we said there are 5 different steps in homogeneously catalyzed processes: ligand dissociation, oxidative addition and reductive eliminations, oxidation and reduction, and nucleophilic attack on the ligands. So what do you classify the first step as? So given 5 choices, you need to pick up a choice. Remember in my notes, if you go back, what did we say about very first step in the homogeneously catalyzed processes? Remember
Would it be ligand dissociation?
Thank you, Chris. That's exactly what is happening here. This is a ligand dissociation here. And this step is a ligand dissociation here because carbon monoxide is getting added. And then we have the insertion processes. So if you see something like this happening, then you must call this as a insertion of ligands. So one of the ligands, original ligands, gets migrated here, and the new ligand gets replaced there. One of the beautiful aspects of this mechanism is this is not out of blue here. People have worked so hard to identify most of the intermediates here. This is the beauty of homogeneously catalyzed processes. So what you can do is you can carry out the reaction, freeze it, and take all the compounds that are in the mixture at any given time and characterize them to see what does that mixture contain, what type of complexes it has. Both by looking at the infrared spectroscopy and also by looking at some magnetic properties, because cobalt is highly magnetic, so it kind of gives you some information about this. And gas chromatography, mass spectra, a lot of stuff people do before. So anytime we propose a mechanism, you must justify the mechanism based on the experimental evidence. So this is not like an arbitrary path. People have worked quite extensively to understand the mechanism before they proposed it. And again, this is the best mechanism we know today. Most of these mechanisms get revised over time because some new evidence comes in and then say, well, maybe this is not exactly happening this way, but in a different way based on the different evidence. So that's all academic curiosity, and the industry loves it. Because once you understand the mechanism, then it gives you some kind of control on how you can improve this, how you can improve the yield or the rate of the reaction. So that's why a lot of work goes on in terms of homogeneous catalysis. And there are several groups in this country. Those of you who are interested in pursuing this can join one of those groups working on the homogeneous catalysis. And you will be asked to design different catalysts. Cobalt is just one example. We have not exhausted all the complexes for these catalytic processes. So, with every time, now and then, we get a new complex doing a much better job than the old one with some advantages. So these things are constantly worked out. All right. Is that okay, folks? Any questions before we go on to, we have several examples. So this is, I thought this is a beautiful example of how this happens. Two reactions, hydrogenation followed by the formation of an aldehyde. Okay, so we'll go to the next example. By the time we end the lecture today, you will know why we were learning so much about complexes. Crystal field theory, ligand field theory, the inertness of complexes, the lability and all that stuff. So these are all reflected in the mechanisms that I'm writing here. So the next one I'm going to write about is the Monsanto process. Monsanto, as you all know, is a multi-billion-dollar company. All that initial money they made by making acetic acid. Monsanto's acetic acid synthesis. Acetic acid, as you all know, vinegar is a very commercially important chemical. And prior to this Monsanto's process, people were doing bacterial reactions, bacterial oxidation of ethyl alcohol to make acetic acid. So Monsanto said, well, let's do this way. We'll take methanol, stuff ethanol, which is used in the bacterial oxidations, but we can take methanol, and if you insert carbon monoxide, right, you get acetic acid because you're basically making CH3COOH. That's your acetic acid. So how do we do this? How can we get this carbon monoxide to insert itself between the CO bond of methanol to make the acetic acid? That is the whole purpose. Bacterial oxidation is okay, but it's a very slow process, and oftentimes, things get contaminated. The bacteria itself gets toxic, because of some of the products, side products. So the efficiency is no more than about 20% there. But here, Monsanto's process, using coordination complexes, you can achieve near 80 to 90% efficiency in terms of converting methanol to acetic acid. So let's now look at this cycle, the catalytic cycle, and see the beauty of making acetic acid from methanol. Okay, this is the overall reaction, so please keep that in mind. All right, so let's start with the process here. In the first one, let me move this go. We take some what we call catalyst precursors. So first thing what we do is we take a rhodium salt, rhodium-3, X could be chloride, bromide, or iodide. It's a halogen. So rhodium-3 halide, so it could be rhodium chloride or bromide or iodide. And then we add carbon monoxide and iodide here. Iodide is not a catalyst, but I would call this as a catalyst promoter. In other words, it improves the efficiency of the catalyst, although it itself is not a catalyst. So when you add this, we get what we call rhodium I2 CO2 minus. So this is diiodal, dicarbonyl, rhodate. What's the oxidation state of rhodium here, folks?
Plus three.
Say,
Plus 3.
is it +3 or +1?
Oh, plus 1. Yeah, the CO doesn't contribute.
Thank you very much. Now we see all the knowledge that we have been talking about is helping us, right? Carbonyl is a neutral ligand. It doesn't contribute to the charge, but there is a 2 iodide groups, but the net charge in the complex is 1-. So the rhodium must be 1. So this complex should be named as diiodal dicarbonyl rhodate 1. This is the catalyst for the Monsanto's process, which made them billions of dollars. Just simple complex. The only problem, of course, is rhodium is pretty expensive. It's a very rare metal. There is not enough of rhodium, but still they were able to use this because this is a catalytic amount and it's always regenerated. So you're not really, throwing the rhodium out. It is a part of the process. So here is how the whole thing begins. In the first step, remember we have methanol plus carbon monoxide, right? So the methanol here reacts with hydroiodic acid. Hydroiodic acid is again a catalyst promoter here. It's not a catalyst, but it improves the catalytic efficiency. That's what a catalyst promoter is. Okay, that's the term that we use. What happens here is we make CH3I plus water. Methanol, watch this carefully, reacts with the hydroiodic acid, which is a strong acid, to form methyl iodide and water. Okay, good. So this methyl iodide now reacts with this complex to give you methyl RH I3 CO2 minus. Now, what is the oxidation state of rhodium here? Chemists always have to keep track of the electrons. We are the accountants for keeping track of the number of electrons. So it's the oxidation state of rhodium. We have now carbon monoxide, I should say CO2, bicarbonyl methyl triiodal rhodate. So obviously when you're adding methyl, it's a negative charge, and there are 3 iodides, the total of 4 negative charges, right? And then you have dicarbonyl, which is neutral with a negative charge. So the rhodium is now 3+ oxidation state. In the previous example, it is 1+. So what happened here now? What do we call this step here? Adding methyl iodide to the complex while oxidizing the rhodium from 1 to 3 and making this complex. Can we call this oxidative addition? Because you're oxidizing the transition metal and then you're adding CH3I, which breaks down to methyl and iodo groups and adds on as 2 independent ligands. So this is an addition that is accompanied by oxidation of rhodium from 1 to 3. See how beautiful it is. Remember, we talked about the steps. One of the steps in homogeneously catalyzed processes is oxidative addition. This is a classic example of an oxidative addition process. So in the exams, Gurveer, they were asking what kind of questions. You don't have to memorize all the cycle, but if I ask you, what is this step here? then you should be able to say that this is oxidative addition. Not ligand dissociation, not ligand dissociation, not nucleophilic attack on ligands, not simple just oxidation reduction, but it is an oxidative addition. Am I clear here, folks? The reason I'm going slow is you have to appreciate every single process and see how beautifully this complex turns the methanol and carbon monoxide to acetic acid so effortlessly. So the next step, one of the carbonyl ligands here gets migrated and gets inserted between the rhodium and the methyl group. So this is migration process, migration of CO. When that happens, this CH3 now one of the carbonyl, so there's only one carbonyl left. So of the two carbonyl ligands in the original complex, one of the carbonyl functional groups gets inserted between the metal and the methyl to give you the acetyl group here. That's the CH3CO, RHCO3CO minus. Now, once one of the carbon monoxide is migrated here, the next carbon monoxide molecule adds on to this, and you get what we call CH3CO, RHI3CO2. So what do we call this step now? Is it oxidative addition, reductive elimination, nucleophilic attack on the ligands, oxidation reduction, ligand dissociation, what do we call this?
Would that be a ligand association?
Chris, you're absolutely correct. That's what exactly it is. Carbon monoxide is now getting added to this complex. So this is a ligand dissociation. That is an oxidative addition. So I want you to recognize the difference between these steps here, right? So moving on, we get this. Here is the beautiful part of the mechanism. Now that you have this, one of the iodo groups here gets migrated here and gets eliminated to form what we call CH3COI. All right. And once that happens, so what's happening here is the iodo group is eliminated. So it's basically minus I and minus CH3CO. These two are gone. So what happens is now you get back to your original catalyst. And that catalyst again enters the cycle. But the beauty of it is, remember in the first step we made water here, right? That water now it reacts with acetyl iodide to make CH3COOH plus HI. That HI is again used here. So you added HI here, hydroiodic acid. As soon as you're done with the cycle, you're making your HI again. So you don't have to keep on adding. This is not a stoichiometric reaction. This is a catalytic process. Similarly, remember we had methyl iodide plus methanol plus HI here. So once the process is done, we get our water back. Whatever the water is used here, this is being used to convert the acetyl iodide to acetic acid and the HI. So after the reaction, the acetic acid is removed. So there are several steps here, and I explained to you the migrations, the insertions, the ligand association, oxidative addition, reductive eliminations, all these things are beautifully depicted here. Questions on the Monsanto process? Anything that's not clear, folks? This is clear? So of course, you can go back and read about Monsanto's process and how efficient this is. These are all important industrial processes. Just in case you're wondering why the hell are we learning in organic chemistry, I think this lecture gives you ample justification for all the concepts we have been learning in coordination complexes, redox, all that stuff. It kind of gives you a beautiful combination of redox and coordination complexes to give you industrially, commercially useful products like acetic acid, vinegar. Okay. We'll get into another one, but before I do this, is there anything that I want to talk about this? I think we talked pretty much of every single step here, the migration, the insertions, and the eliminations and all that stuff. Great, okay. The one that I want to ask you is, what do we call this step here? So in the exam, these are the type of questions that we say. We'll say, let's say this is the D, and ask you what is D? Is it ligand dissociation, oxidative addition? I mean, multiple choices. So what do we call this? What is happening in this process here? We are losing CH3CO and one of the I's. And what is the oxidation state of rhodium here? So rhodium 3, right? So, and rhodium 3 is now getting converted to rhodium 1. In the process, we are eliminating the acetyl group on one of the iodides. So I think now I'm giving you the hint, what we should call this. There are two things happening. One is yes, Michael.
Yeah, it's reductive elimination.
Absolutely wonderful. That's absolutely correct. That's exactly what is happening. There is an oxidative addition in this step, and there is a reductive elimination in the final step. In between the oxidative addition and the reductive elimination, you have the migrations, insertions, and ligand associations. Those are the steps that are in the process. Is this clear to all of you folks? All right, so let's look at another homogeneously catalyzed, industrially important process. The reason I'm drawing all these things is some of the textbooks don't give you the whole picture of the process, kind of shortcut, and might be a source of confusion to some of you. That's the reason why I'm writing this down and explaining every single step that goes on. All right, here is another one. Rapid oxidation of alkenes. Okay. So if you want to commercially make acetaldehyde, it is how you make it. You take ethylene gas, react with oxygen, in the presence of palladium chloride. Palladium chloride is the catalyst they use, and we make CH3, CHO. That is the oxidation of olefins into aldehydes. If you don't have the catalyst, hydrocarbon plus oxygen always gives you carbon dioxide and water, right? So what a catalyst does is it alters the process path in a way it selectively drives towards the oxidation to make your aldehyde. And one of the beautiful aspects of this process is if you do not control this, this oxygen can also oxidize acetaldehyde to acetic acid. But in a vacuum process, that doesn't happen. The reaction stops the formation of the acetaldehyde. This is how the aldehyde is produced commercially, palladium chloride. So, well, in most of the organic textbooks, when you read this process, vacuum oxidation, that's what you see. But that's not the whole story. The whole story is more complex, at the same time more beautiful. So let me go through this process, how this happens. So in the first step, what happens is, that's the first step, C2H4, which is ethylene, reacts with palladium chloride and water. This is an aqueous solution. This is a homogeneous catalysis, right? We get CH3CHO, and we get palladium in zero oxidation state. So we get elemental palladium plus 2HCl. That's the first step. So we have ethylene reacting with PDCl2 in the presence of water. So what ethylene does is kind of reduces the palladium from 2+ oxidation state to 0. So you get elemental palladium and aldehyde. Is this a catalytic process, folks? When I say palladium chloride is the catalyst, in this reaction, isn't it true that the palladium chloride is consumed and gets converted to HCl and palladium metal? No, it doesn't sound like a catalytic process because you started with palladium chloride and you should get palladium chloride on the right-hand side. That's not what is happening. You get elemental palladium, right? So the next step that happens is this oxygen now reacts with the palladium metal to give you back the palladium 2. So this elemental palladium here is now oxidized with the external oxygen to give you palladium 2, and the palladium 2 again enters the process. The ethylene reduces the palladium 2 to palladium metal, and so there is a chain reaction between 1 and 2. So they alternate infinitely to make the product. So the problem is this oxidation of palladium by oxygen is slow. This is the bottleneck here. So if you want to make a lot of acetaldehyde, you need to somehow catalyze the second process because it is slow. So what do the industry people do here? So what they do is they take the palladium and then react with tetrachlorocopper 2 complex, and that reacts with the palladium metal to make palladium 2 plus PD2 plus. That's the palladium is oxidized by the catalyst, and the complex gets reduced to plus 4Cl minus. So what happened here? The palladium gets oxidized to palladium 2 plus. This copper in the original complex was in the 2 plus oxidation state. Now, when you go back to this complex, cuprate complex, this dichlorocuprate, copper is in 1 plus state here. So this is 2 plus, and that's 1 plus. So what's happening now is the redox is facilitated by the oxidation of palladium to 2 plus and the copper getting reduced to 1 plus. So this is not a direct oxidation of palladium, but using this complex. Now, in the second reaction, this 2 copper chloride 1 reacts with 1/2 mole of oxygen and 2H plus 4Cl minus, which we have here, to give you 2CuCl4 minus 2 plus H2O. That complex again goes back here. So it gets regenerated in the second reaction, consumed in the first process. So these two processes are infinitely faster than the simple oxidation of palladium with oxygen to make palladium 2 plus. Although, of course, it is possible, but using this complex enhances the rate of the process so nicely that it is industrially feasible to make acetaldehyde. So this is another example of so much of redox chemistry going on, redox chemistry of the coordination complexes, and the ability of the copper to exist in 2 different oxidation states, and then going back to the ethylene, reacting with the palladium to make your palladium metal, and the palladium metal, instead of getting oxidized directly with oxygen, there is a secondary process that goes on where the complexes, chlorocomplexes of copper, shackled between 2 and 1 plus state, making this happen. Questions up to this point, folks? So what should we call this chlorocomplex here? Is it a catalyst or a catalyst promoter? Any thoughts on this?
I'd say it's a catalyst promoter.
Chris, you are absolutely correct. The actual catalyst is PdCl2, but what copper, the chlorocomplex of copper does, it does enhance the efficiency of the palladium by creating an alternate pathway in which the oxidation of palladium is made extremely simple. So the test for this, if I don't use palladium chloride but use copper chloride, does the reaction go? No, it's a palladium that does the catalysis. But what the chlorocomplexes of copper do is they enhance the efficiency of the catalyst. So they're called catalyst promoters. Okay. So in the world of catalysis, there are catalyst promoters and there are catalyst poisons too. Sometimes if you're adding a different compound, it diminishes the ability or the efficiency of a catalyst. Okay, they are called catalyst poisons, which kill the efficiency of a catalyst. On the other hand, catalyst promoter is one that enhances the catalytic efficiency of the catalyst. So there are lots of terms when you are in the business, you will hear catalyst poisons or catalyst promoters. Sometimes you also use negative catalysis. A negative catalysis is basically a catalyst that reduces the speed of a process. So most of the positive catalysis all by itself is a positive catalysis. In other words, it improves the rate of reaction. There are some reactions you don't want to go too fast. So in which case you can design a material that slows down a process. So those are called the negative catalysts. For example, if a patient had a snake bite and the poison goes very quickly and you don't want the reaction to happen very quickly. So you can design a negative catalyst that will cut down the rate of infection, for example. So those are all different areas. But I don't want to confuse you with all those things, but this is basically an idea about how the topics of coordination complexes and the redox chemistry help us to develop new homogeneously catalyzed processes. Any questions up to this point? All right, so this is how far I would like to do in the homogeneous catalysis. In my next lecture, we will talk about heterogeneously catalyzed chemical processes, which are also equally important as homogeneously catalyzed processes. Sometimes you may have two different processes, one for homogeneous, one for heterogeneous. A lot of times the industry prefers a heterogeneous process, and we will talk about heterogeneous catalysis in our next lecture. Okay, but before I close this presentation, are there any questions so far? We've given you several examples of industrial processes, explained to you the process, the mechanism, and the steps. So please read the heterogeneous catalysis section for the next lecture, and we will see you day after tomorrow, right? Thursday. Okay, if there are no questions, we will see you Thursday.